Have you ever wanted to build walls around you to keep out noise? Or maybe a wall to protect San Francisco from the earthquakes produced by the pesky San Andreas Fault? Would you be surprised if I told you the way to do so wasn't so different? Here we will be discussing how metamaterials could be the answer to both issues. To give you a better understanding of how to stop sound waves or seismic waves, first we need to convince you that they are the same by introducing the topic of pressure waves. Then we will get into how they interact, and lastly why there isn't a big anti-earthquake wall around San Francisco already, and new metamaterials that could offer solutions. Sound is the propagation of a pressure wave through something, most of the time air. Let's look at how these longitudinal waves are created in this pipe model. The piston pushes the air molecules closer together, creating an area of high pressure. As it moves back, a vacuum produces an area of low pressure. The piston will push again and again as it vibrates, creating other high pressure regions. The distance between these regions is the wavelength. The amplitude, which controls the loudness, can be expressed as a function of time and position in the x direction. The wave is also controlled by the wave number k and the angular frequency omega, which are functions of frequency and the wavelength. Check out this video of the guitar string in slow motion. Here, instead of a piston, the string pushes and pulls the air over the hole as the wave travels up and down the guitar, creating high and low pressure areas. It is important to understand that pressure waves travel at many different frequencies, which has a large effect on how it will act. For example, submarines see underwater at very high frequencies, similar to how bats see, so high that they are out of the human range of hearing. And then there are seismic waves that have such low frequencies you do not hear them. Now, as pressure waves move, they often come in contact with surfaces, like a wall. When a wave strikes, it will be transmitted or allowed to pass through, reflected, or bounce back, and some of it will be absorbed by the material, and its energy will be dissipated as heat. All three will happen at the same time, in the different ratios based on the material they are impacting. This is called the absorption coefficient, or alpha. It is between 1 and 0. An alpha of 1 means that all energy is either transmitted or absorbed, and none is reflected back. 0 would mean that all energy is reflected. The coefficient of absorption is governed by Stokes Law. In this law, the most important factors are wave velocity, which is often controlled by the medium, and the angular frequency. Alpha determines the amplitude of the wave that is transmitted through the material. In order to have a thinner material or a smaller d, you will need a larger alpha to get a small amplitude. The transmitted wave with a smaller amplitude means that energy was absorbed or reflected by the material. Foams are used to absorb sound because of their low density and high elasticity. You see them in studio rooms all the time. These combine two mediums, the polymer and air. However, thick foams are needed and still do not provide efficient sound absorption. This study of polyurethane foam found that the absorption coefficient is close to 0 at low frequencies. So why are low frequencies so difficult to absorb? Because of their high wavelength, they have lower kinetic energy. Since they don't have enough energy to elastically deform the material, this allows them to pass through solids. You've observed this if you've ever been standing outside a nightclub. The only thing you hear is the bass. New metamaterials are being developed, engineered to absorb and reflect low-frequency pressure waves. This average-looking panel, developed by French researchers earlier this year, boasts the ability to absorb low-frequency sound waves. The panels are unique, different from random air pockets seen in the foam. These panels are made up of repeating patterned sets of inclusions or holes filled with air. These inclusions are usually on the order of the wavelength they are attempting to affect. They interact with the pressure waves differently from the surrounding material, because the air and the material have different mechanical properties. How the wave changes depends on the material, the shape, the size, and the pattern of the inclusions. An acoustic metamaterial will reflect, absorb, and/or bend pressure waves differently for every frequency, so a metamaterial can be tuned to a specific frequency. The same concept is used for seismic waves, but scaled up. Researchers propose using metamaterial cylinders drilled into the ground. The plastic or metallic cylinders will be surrounded by a concrete outer shell with holes to dissipate the energy, and arranged in several concentric rings surrounding the building in an underground wall. Each ring can be precisely tuned to a different frequency, allowing the structure to affect a range of seismic waves. A proof of concept was performed. Utilizing a vibration generator and various sensors, the team created a grid of 5 mm deep holes in the ground in an attempt to simulate the effects of wave damping cylinders. Their results were impressive. The area around the vibration source contained roughly 2.3 times more vibrational energy after the boreholes were made, showing that the structure had reflected the vibrations back to the source. You may be seeing an increase in the number of walls. Let's just hope they're made of many materials.